In this lesson we're going to look at how to polarize a conducting sphere. So imagine that we have an aluminium conducting sphere in front of us on an insulating handle, and first of all we know that this metal conductor, this aluminium conductor, consists of an enormous number of positive aluminium ions. Okay, this is a metal surrounded by a sea of free electrons. And so the first important point is that in the conductor the positive charges are fixed in the nuclei of the atoms. They cannot move anywhere. They are stuck within the metal lattice. They can't go anywhere. The charges that move in a conductor are always the electrons. And so when we polarize this conducting sphere, it will be the electrons, that's to say the negative charges, that do the moving. The positive charges, which are the protons stuck in the nuclei of the atoms or the ions, will not do any moving. They will be fixed. So the total charge on the conductor at this moment is 0. And in this polarizing process, that total charge is never going to change. It's always going to be 0. What's going to happen is that the charges are going to become separated, but the total charge will never change. That will always be 0. Okay, so let's polarize this conducting sphere, and to do that I'm going to take a balloon and I'm going to rub the balloon against my hair. Okay, rub, and when I do that, negative charges are going to jump from my hair onto the balloon, and the balloon will become charged negatively. So I then take my balloon and I bring it near to the metal conducting sphere. Right, I'm not going to touch the sphere, I'm just bringing it near to the sphere, and what will happen then is that the negative free electrons that are near to this side of the sphere, that are near to the balloon, will be pushed towards the other side of the sphere. So we'll do that. Some of them get pushed over to the other side of the sphere, and because these came from this side of the sphere, what will happen is that we will be left with positive charges near to the balloon. So this side of the sphere is charged positively because these negative charges have moved over to the other side. And so, as I said before, the total charge on the sphere has not changed. It is still 0. It's just that the charges have been separated, and locally one side of the sphere is charged negatively and the other side is now positively. Now then, we can do exactly the same thing with an electroscope, and an electroscope is a useful device that can be used in the laboratory that helps us to measure, or gives us an indication of the amount of charge that's present on an object. So just let's have a look at that. So let's just quickly describe the electroscope before we perform our little polarizing experiment. You can see it consists of a metal conducting plate and a metal support. These are separated from the casing of the electroscope, which is usually a glass casing, by some insulating material here, and attached to the support we have a gold leaf, piece of gold leaf, which is free to move, and behind that gold leaf there is a scale which indicates the amount of charge that we are testing. Okay, so let's just remove the gold leaf for a minute. Let's suppose that we have again a plastic or perspex rod or ruler, and I rub that ruler against a duster. Then negative charge will jump from the duster onto the perspex rod through friction, and I'm going to bring that rod near to the electroscope plate. Okay, and as I do so, I will observe my gold leaf moves away from the support. So why does that happen? Well, that happens because, as with the balloon and the conducting sphere that we've just observed, when these negative charges come near to the plate, negative charges from the plate will be pushed downwards. They will push away from the plate to the supporting stand and onto the gold leaf. And as a result, these charges will then repel each other and push the gold leaf away from the support. And by the degree of deflection, we can then have an idea of the amount of charge that's present on the object that we're testing. While these negative charges are pushed away, that will leave the disc, the conducting disc at the top of the electroscope charged positively. Again, repeating, we have not charged the electroscope here. All we're doing is we're polarizing it. We will look at how to induce charge on the electroscope in the next lesson. Just to repeat myself again, the total charge on the electroscope here is 0. Right, all we've done is we've just separated charges. Now let's take a slightly different situation. Supposing I have the same perspex rod with the same charge on, but I bring it nearer to my electroscope. What will happen is, because the electrostatic force increases as the distance between charges decreases, okay, more electrons will get pushed down onto the supporting stand and onto the gold leaf, leaving more positive charge on the conducting plate of the electroscope. And as a result of that, you can see that the gold leaf is deflected by a greater amount. Now, if we were to repeat that experiment, bringing the rod to within the same distance but increasing the amount of charge on the perspex rod, well, that would again increase the amount of charge pushed downwards onto the stand and onto the gold leaf, causing an even greater deflection. So you remember, you can get a negatively charged object by rubbing a duster against a perspex rod. Now, if I wanted to test a positively charged object and see what happened, then what I would do is this. Instead of using a perspex rod, you'll remember that we would use a glass rod. And rub that against a silk cloth. So the ideal thing for this would be a pair of glasses. Get a glasses case, and most glass cases come with the glasses inside and a silk cloth to clean the glasses. So if you take that silk cloth and rub it against the glasses, you will charge the lenses of the glasses positively. So what we've got here is a glass rod that's been charged positively, and as a result of that, when we bring that near to the plate of the conductor, what happens now is that electrons, instead of being pushed away, will be drawn towards the glass plate from the conducting support and the gold leaf, causing the plate to be charged negatively and leaving the support and the gold leaf charged positively. Again, positive charges will repel, causing the gold leaf to be deflected, and the amount of deflection will indicate, either the amount of charge on the glass rod, or will also be affected by the distance between the rod and the conducting plate. And so, we get a repeat of the previous experiment, except now the support and the gold leaf are charged positively and the plate is charged negatively. So here, more negative charges are drawn to the electroscope plate because the glass rod is nearer, and here even more charges are drawn to the plate because there are more charges on the glass rod. I should have drawn, that should have been a little bit further away actually. And that's left more positive charge on the support and the electroscope here, and even more here, causing a bigger deflection. So in the next lesson, what we're going to do is look at how to charge an object by induction.